Welcome back. Good morning. We're talking about Bayes thinking, Bayes updating, priors, posteriors, likelihoods, independence, and conditional independence. And of all these terms, actually the one that I want you to spend the most time thinking about is conditional independence. It's going to feature very prominently in many of the coming weeks. So let's remind ourselves what conditional independence is about and in what way it differs from regular independence. Just to remind you, x and y are independent means that for every x and for every y, p of x comma y equals p of x times p of y. Now I want to write it in one more way that you will often find. This is the same as saying, alternatively, that p of x conditioned on y is p of x. Or again, alternatively, that p of y conditioned on x is p of y. These are all different ways of saying the same thing. So you should be used to seeing them all. And I put the line here to mean all of these should be interpreted relative to for every x, for every y. For every x possible, for every y possible. Now, conditional independence is the same thing, only you add a conditioning event, and you have to quantify over all possible conditioning values. So x is independent of y, conditioned on z means for every x, y, and z, p of x comma y given z is p of x given z times p of y given z. And you can see regular independence as a special case where the conditioning random variable is null. You're not conditioning on anything. And I also mentioned that you can think of x as a set of random variables, y can be a set of random variables, and z can be a set of random variables. So the most general statement is some set of random variables is conditionally independent of another set of random variables conditioned on some other third set of random variables. And I want to write this again in the same spirit as this. This means the same thing as probability of x conditioned on y and z equals probability of x conditioned on z alone. Or probability of y conditioned on x and z means probability of y given z alone. So it's basically saying in the right context, the way x depends on y is it doesn't depend on y. You can cross out the y. Whether you condition on y or you don't condition on y, it's the same value. Whether you know y or you don't know y, it's the same value. Remember the information theory view of this? This is the same as mutual information between x and y conditioned on z, and this is just mutual information between x and y. Saying they're zero is the same as saying this is independence. And as we saw in the case of information theory, the right-hand side does not imply the left-hand side, and the left-hand side does not imply the right-hand side. In fact, if you change z to a different random variable, z prime or w or anything else, again, all bets are off. What wasn't true can become true, and what was true can become not true. These are all different statements. I want to give you a few examples. I'll give you the example, you tell me where it belongs. X is drawn by flipping a coin. Okay, so x is a binary, a Bernoulli variable with probability half of being 1 and half of being 0. Flipping a coin. Y is also drawn Bernoulli flipping a coin, drawn with a separate but identical process. And Z is defined as X XOR Y. Are X and Y independent? You've seen this. We've dealt with this many times. Are X and Y independent?
Yes.
Thank you. A few other enthusiastic, yeah, sure, of course. Wake up. Yes, X and Y are independent. So this is an example of X and Y are independent. What about, are X and Y independent in the context of Z? Conditioned on Z. Are X and Y condition independent, conditioned on Z? The answer is definitely not. We know that immediately from information theory. If you know Z, then X tells you everything there is to know about Y. So you can and you should be able to move back and forth freely between information theory and probability, which means you can write down without even calculating that P of X and Y conditioned on Z is in general not equal to P of X conditioned on Z. So all this is not independent times P of Y conditioned on Z. When I say in general, I mean that when this independence doesn't hold, that means that there exists some values of X, Y, and Z for which this is true. It doesn't mean it's true for all X, Y, and Z, right? The negation of this statement is that there exists some X, Y, and Z such that P of X comma Y given Z is not equal to P of X given Z times P of Y given Z. All right, remember that if X and Y are independent, if they're not independent, it doesn't mean that this inequality holds for any value of X and Y. Right? It means it holds for at least one value. In the case of binary random variables, it'll show that it holds for all of them. But you can immediately make this statement from this statement. At least put the there exists symbol there. All right, let's do another example. Let's do an example closer to the example we discussed of cancer. Let's say there's a test for a condition, and the condition is fairly common in the population. So our hypothesis space would be what condition is equally common in the population, in human population? What things happen about equally? I'm sorry? What kind of diabetes? Asthma and diabetes. Complicated conceptually. Let's just fast forward to 20 years from now and say obesity. Okay? But that's visible. I'm looking for something that's not variable. Let's take diabetes. Diabetes. Not diabetes. So let us assume for simplicity that half of the people on the planet have diabetes and the other half do not. So these are our hypotheses. This is our random variable, so to speak, and there's an h, the small h, the values that it takes. And there's a test. Test can take on values positive and negative. Now, very similar to our case of cancer, the test is highly accurate. Let us just say that the test is 99% accurate. Equally so in both populations of diabetics and non-diabetics. So if I wrote it down in the likelihood table, here's somebody who's diabetic, somebody who's not diabetic, and here's the test being positive and being negative. And we would have a diagonal here of 0.99 and 0.01. I'm sorry, 0.99 here too. 0.01 and 0.01. So for someone who's diabetic, the test 99% of the time says yes, and 1% of the time says no. For someone who's not diabetic, it's the other way around. Okay? Now the tests, the way the test is done, it's actually 100% accurate test. But the technician on the way out of the lab flips a coin, multiple coins. And in other words, there's some random process that's not dependent on anything else, that 1 in 100 gives you the wrong result. Okay, somebody mistyped the letter Y instead of the letter N, or something like that. All right, now let me ask you about the tests. You have two tests. Is test 1 independent of test 2 conditioned on diabetes, on whether the person has diabetes or not? So among all the people who have diabetes, what kind of a sequence of tests do you expect to get? Positive most of the time. Once in a while, once in 100, you'll get a negative, right? Now, if you know the person has diabetes because you did other tests and you're 100% sure they have diabetes, you bring them to be tested, they got a positive test. You do another test, do you expect it to be positive or negative? Positive. What are the chances you give it of being negative? 1%. Suppose it did come back negative. You do another test. What do you expect? Positive. Probability of negative would be 1%. It will remain 1% versus 99% no matter how many tests you do, right? Because the underlying cause is that they do have diabetes. If you know for sure that they don't have diabetes, it's the same story. You expect it to be negative almost all the time. And the fact that you got some tests being positive doesn't affect the fact that you're going to get some tests negative. So, by the story that I told you about how the errors are produced, we can conclude that given the truth, given the real hypothesis, any two tests are independent of each other. So this is an example of conditional independence. Conditioned on the disease state, tests are independent. What do you think about this? Is this true? No, we're not talking about knowing the truth. We're talking about a person coming in and the same person is having two tests done. Let me ask you, before you resolve this, what is the probability of T1 being positive in general, in the population? If you're just sitting in the lab and waiting and grabbing one test that came off the production line, what is this probability of being positive? I'm sorry? 50%. Why is it 50%? Okay, yeah, you're waking up. I hear responses. I don't even hear what they are, but I'm sure they're correct because you look like you know what you're saying. But that's good. Yeah, okay. It is 50% because there's a 50% chance that they're diabetic, in which case 99% of that time you'll get a positive. And there's a 50% chance they're not diabetic, in which case there's 1% chance. So you can calculate that. This is P of diabetic times P of positive given diabetic plus P of non-diabetic times probability of positive given non-diabetic. And this is 1/2 times 0.99 plus 1/2 times 0.01. And this comes to 1/2. So the probability of any one test is 1/2. I designed it that way. Probability of any other test is also 1/2. Now, what about the probability of two tests from the same person? Are they independent of each other? If they were independent of each other, we can say right away that the probability of two tests from the same person coming back, any answer would be a quarter. Positive, 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 negative, negative, positive, negative, negative. Right? They're all equally likely. They're independent. Yeah, it's like two flips of a coin. Is that what you expect? No. If you randomly pick a patient and have two tests done on them, you expect that it will be the same outcome most of the time. in both tests, because it's a very accurate test. Right? How often will it be the same outcome, roughly? Can you calculate how often will it be the same outcome? About?
98.
99? What was that?
I was thinking it would be 98 because 99 times 99. So it's 98.
Yeah, so it'll be about 98. One way to think about it is to say there could be an error in the first test, or there could be an error in the second test, and in both cases you would get wrong result unless there's an error in both cases. Right? So a positive followed by a negative, there's for a diabetic, there's a 1% chance that the second test is wrong, 1% chance that the first test is wrong, and 1% of 1% chance that they're both wrong, in which case both labels would look the same. But yeah, about 98 is the right answer. So they are not independent. Now this is the cutesy example. This is what will happen a lot in the real world. So spend time thinking about this. Why is it the case that they are not independent? They appear to be dependent, but once you condition them on something that explains them, they can become independent. This is very strongly ties to the notion of how do you infer causality. Here's another example. I don't know if it's famous, but it's my favorite example. A scientific study question.
Is that like still two tests on the same person?
Yes, two tests on the same person. Yeah. Tests of independent people are independent. Good point. Yes?
98% of the time, like the 2%, we can't predict if both tests will be the same or not. So how can we say that it's always true if they are not independent variables?
I'm sorry, I did not understand the question. Why do I say that it's always true? So maybe it's related to the question that was just asked. I defined my T1 and T2 to be two tests on the same person, but a person whose disease state I do not know. I don't know if that answered your question. It probably didn't. If you restate it a little louder, I will try again.
So, if 98% of the time they are bound to be true, bound to be the same for a single person, but the 2% of the time they are not, right? So if we know the outcome of test 1, we cannot predict with 100% surety that this is the result.
Right.
So in that case, how are we saying that it's independent of test 1?
Okay, you're describing a scenario where you already know the result of the first test, and now you're expecting the result of the second test, and you have quite a bit of knowledge about it. You can suspect with high probability, about 98%, that it'll be the same as the first test. And now you're asking, how can I say that they are independent? That they're not independent. How can I say this? I'm not thinking of the answer, I'm thinking about the question. For me to say that they're not independent, I need to show that there's at least one set of values, positive, negative, and so forth, that the probability of the product is not the same as the joint probability. Right? So let me do that. Let me go through this example completely. The probability of test 1 being positive is 1/2. The probability of test 2 being positive is 0.5 also, and also negative, it's the same thing. The probability of test 1 being positive and test 2 being positive is what? I can break it down by the disease state of the person, right? This is what connects them. So I'll do the same as I did there, only for two tests. It's the sum over diabetic and non-diabetic of the probability of test 1 being positive given diabetic. Well, I'll just write it explicitly. If I introduce summation, I have to introduce another variable name. So where are my erasers? Times probability of T2 being positive given that the person is diabetic and the test 1 was positive. This is the chain rule with the extra condition of diabetes. And then I have to add the second part, probability of test 1 being positive given not diabetic times probability of test 2 being positive given, again, not diabetic and the test 1 was positive. This is using the chain rule or the law of total probability to open it up. Now I'm going to use the property of conditional independence, the critical property here, to say that once I condition on the fact that the person is diabetic, this doesn't matter anymore. This is the story I said before about the process by which the error is generated. The error is generated in a process that does not, that at least once you know the state of the patient, it does not depend on the previous test. In fact, the story I told was stronger. The error is generated in a way that's independent even of the disease state, right? You screw it up whether you're diabetic or not. But you don't have to go that far. You can just make the statement that if you know the disease state, there's a 1% chance of error regardless of whether the test before was erroneous or not. Whether the test before was an error is not going to affect that. So the critical part is now saying I can get rid of this, and for the same reason, I can get rid of this. And now I can add it up. This I know is 0.99. Did I forget to put the priors? Yeah, I forgot to put the priors. If you were just too polite to correct me, I'm happy. But if you didn't notice it, I'm not so happy. There's a probability of diabetes here. And there's a probability of diabetes here. Probability of non-diabetes here. So now I have 0.5 times 0.99 times, again, 0.99 plus 0.5 times 0.01. If he's not diabetic, there's a 1% chance of getting a positive result, times, again, 0.01. So what I have is 0.5 times 0.99 squared plus 0.01 squared. The 0.99 squared is what you guys were referring to before as about 0.98, 98%. And this is a tiny correction, the chance that both tests are wrong. In that case, they will agree. I don't know if I answered your question. I suspect I didn't, but at least I spelled it out. We can look at these two tests in a slightly different way. We can pretend that these two tests were one test with two outcomes. Well, actually, two labels, therefore 4 outcomes. Okay? So let's say the doctor is very suspicious of the test, that he doesn't trust how accurate they are, so he says, go do the 2 tests one after the other. Don't even wait, don't even bring me back the first test, just do both of them. So you can think of them as a single test, a single combined test, in which case you can think about their likelihood function. The likelihood function will consist now of 4 possibilities: positive, 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 negative, negative, positive, and negative, negative. And here you can be diabetic or non-diabetic. If you're diabetic, what is the probability of 2 tests coming back positive? I didn't hear it, but I assume you're right, 0.99 squared. The probability of the first test being positive and the second one being negative is 0.99 times 0.01, right? So it's 0.99 times 0.01. And this one is exactly the same, but reversed, 0.01 times 0.99, and this is 0.01 squared. And this is going to be exactly the opposite, 0.1 squared, 0.01 squared, 0.99 squared, and this happens to be the same. This is 0.01 times 0.99, and 0.99 times 0.01. So these actually happen to be the same values. Switch sides? All right. Now what I like about this table view is that if it turns out that the tests are not independent, we can modify the table. Why might the tests not be, well, I already told you they're not independent, but until now we assume they're conditionally independent, conditioned on the disease state, right? Why are they conditionally independent, conditioned on the disease state? Because for a diabetic, for the story I told you, the reason there was a mistake was some random, unrelated event that happened on the way out of the lab. But why are lab results not always correct? What are the causes for lab results not being correct? Think about the cancer example. Or any other example, any test that you may have had or know about. Why are they sometimes incorrect?
Technician error.
Technician error. Okay. Technician error is they just didn't do the process right. I'm sorry, let me write it down. Technician error. Say it again. What was it?
Disease rate is small.
Disease rate has fallen.
Is small.
Is small.
Cancer is very rare. A particular cancer is extremely rare.
A particular cancer is extremely rare. Is that a reason for the test to not show the truth? That's what I'm asking about. I'm asking what makes a test not give you the truth? Yeah?
A lot of times they're designed for most of the population, but some people have genetics that throw the test.
That's right. That's a good one because it's going to play havoc with what we're doing. Tests are developed to be accurate on the population as a whole. Sometimes they work by checking the level of some chemical in your blood or some other compound. But people are all different, and some people may have the disease but not have that chemical. Okay, so cancer is characterized by particular chemicals circulating in your blood, let's say, but some people might have that particular cancer that is usually associated with that chemical, and yet they don't have that chemical. So the tests don't really test directly for cancer. They test for a proxy, for something that usually shows up with cancer. And for some people, they may not show up together. So individual idiosyncrasy, that's a fancy word. Idiosyncrasy, spell it right? Syncrasy. Basically, we're all unique. We're all special. It could be the genetics. It could be something else. It could be epigenetics. Something in there, how they formed. It could even be something that happened later in life. Somebody is on another medication and that medication masks or disables the production of the chemical that the test is looking for. What's important about this is that this is a fixed fact about the person, which means it's not a random draw every time you take a test. It's a random draw every time you pick a person. Once you pick the person, you fix them. They fail the test once, they'll fail it again. That's important. Not necessarily. I'm sorry?
People may not comply with possible requirements.
Right. Oh. Right, so you're saying so there are also individual tendencies that are going to be probabilistic. Some people are more careful about following instructions before they take a test, and some people are less careful. If everybody was completely careful, picture would be easier, but people who are less careful are more likely to get an error in their test, but not necessarily the same probability every time they take the test, because sometimes they are, they complied and sometimes they didn't comply. Sometimes the test was done early in the morning, so they didn't eat, and then other times they were done in the afternoon, and by then they ate even though they were not supposed to. Okay? So individual idiosyncrasies, it could be genetic, epigenetic. Epigenetic means it is not evident statically in your DNA, but it is nonetheless in the state of your genes, your gene expression status. It could be behavioral. All right, give me other reasons for errors. Yeah? The test does not include critical factors that actually cause the result. But we're assuming it's the same test always, right? So it doesn't include those factors, meaning it will always be wrong? Or I'm trying to explain why tests are sometimes wrong and sometimes not. Well, maybe there's still something there.
So it only includes like some of the other factors,
Okay, let me modify it slightly. Let's say that the cancer we're interested in, or the diabetes we're interested in, is actually not one disease. It's multiple diseases. It's multiple types of diseases, and they're all lumped together in our eyes. Diabetes, we know there's type 1 and type B, and they're actually type 1 and type 2, and they're actually quite different from one another. Maybe the test is, and maybe there's a type 3 that we're not aware of, that have similar manifestation. We lump them together. It appears in only 2% of the population, or one half of 1% of the population, and the test doesn't pick it up. So that falls in your category. So that would be, it could be under individual idiosyncrasy, okay, disease idiosyncrasy, disease variation. Give me more reasons. Somebody else? Sorry? Machine error. Okay. Good. Let me stop here. I have all the types I need. Now, given that there's a test that has all these kinds of errors, would two successive tests be conditionally independent of each other, conditioned on the disease state of the person? Or let me ask you simpler questions. Suppose there are 4 different tests, each one subject to separate one of these 4 errors. Which of these would be conditionally independent, conditioned on the disease, and which will not be conditionally independent? Remember that we're always talking about the same person. So it's conditioned on disease and the person. 2 successive tests. Let's start with this guy. The poor guy or girl who, because of their genes or because of some other medication they're taking, the test just doesn't pick them up. It's not sensitive enough. Would you say that 2 successive tests for the same person would or would not be conditionally independent, conditioned on the person and the fact that they have the disease? conditionally independent for the most part. I mean, you could come up with a story why they're not, if there's a variation in the person, but yes, generally from the simple story I told you, they are conditionally independent. You fix the conditions that explain the error. They're not changing. Therefore, whether you make a mistake, whether you get the erroneous answer once, wait a minute. It's supposed to fix me if I'm wrong. If you fixed it, then you get conditional independence. Yeah. Independence. Okay. So this would be T1 conditionally independent of T2 given the disease and the person. P for person. What about disease variation? Yeah? Let me hold it. Let me just get the answer to this question and we'll come back to you. Okay? The error is only because some type of diabetes is not picked up by the test. In fact, if the error is only because of that, and the same as the individual the idiosyncrasy, if the error is only because of an individual idiosyncrasy, a genetic makeup, or because of disease variation, these don't change from T1 to T2, and the disease condition does not change from D1 to T2. Therefore, you will get exactly the same answer. So it's an extreme case of independence in the sense that they're constant. But let's make it a little more realistic. Let's say that there's always some kind of probability of another kind of error, like flipping a coin on the way out. So there's like completely random error that's on top of it. At least the part of the error that comes from these factors, you can say are conditionally independent because these factors don't change. All right, now I'll go back to your question.
Calculating the probability of both tests being positive, and it's like around 98% for the point, 98%. And does that mean like doing two like tests instead of doing one test is like has like a lower accuracy?
That's a very interesting question. The question is, let me repeat it. If you do one test on a person who's diabetic, there's a 99% chance to get a positive. If you do two tests, the probability that both of them will be positive is around 98%. Does that mean doing two tests is less accurate, did you say? Less accurate than doing one test? Kind of a tricky question. So whenever you find you get a tricky question, go back to the definition. What do you mean by accurate? Less informative? Is it more informative to do two tests or one test? I think intuitively it's more informative to do two tests. In fact, we know from information theory that once you did one test, there's some amount of an entropy left in the disease state, and then doing the second test cannot make it any higher, on average. On average. So no, the answer is it's more informative to do two tests. But you equated two positives with a positive. You could also choose to equate negative positive or positive negative with a positive, right? You have more refined answer. You have 4 answers to deal with rather than 2. So the comparison is not so clear. So you have to think what you mean by accurate.
I think if you're conditioning D1,
Yes, I would agree. If you ask how much information you get about D from the 2 tests.
if you ask 2 tests given D, I think you get less information.
So you are looking at the mutual information between the disease and the 2 tests together? I'm sorry? Probability of D given plus plus, and you're comparing it to probability of plus plus given D. Of D, right, but then later you're comparing it to this. So you're saying this is bigger than probability of D given just 1 plus, right? So Getting 2 positives increases your confidence or your probability that D is correct. But what did you say about this?
Like this is less, but it doesn't. This is not really what we're testing.
This, I'm sorry?
Like we're trying to get easier from tests, not tests from physics.
Right. Okay. All true. Let's go back to this, and specifically let's look at these. Would you say if the only sources of error are, say, technician error plus some random noise, would you say 2 tests are independent or conditionally dependent, or conditionally independent, condition on the disease and the person? I'm sorry? They are dependent. Why?
Is the random noise essentially?
So the random noise is just to make sure that once you're conditioned on the things that matter, there is still some randomness. Mathematically speaking, I don't have to have it there. It becomes, once you condition on the causal event, on the cause of the error, the test becomes 100% chance of being one way and 0% chance of being another, so it's trivially independent. I added the random noise just to keep it a true random variable, not a degenerate random variable. So, if the source of error is technician error, conditionally independent or not conditionally independent? Don't give me an answer, give me a question.
Does the technician always repeat the same error?
Yeah, well, no. I don't know what you want. Is it the same? What I was hoping to hear is it the same technician? So to answer questions of conditional dependence or independence, you need to really understand the process. You need to understand the causality and what is held fixed and what is variable. In the real world, medical tests will have errors due to any of these. Some of these will remain the same when you repeat the test. Some of them will not. Therefore what? The overall effect is conditional independence or not conditional independence? Not conditional independence. But you can move them more towards conditional independence by trying to vary. So you should send the test to a different lab. You will get rid of that source of error. Or you should at least insist that a different technician does that. Or do a different type of test. Doing a different type of test will address this problem and maybe this problem. Sending it to a different lab will address these 2 problems. I want to introduce another notation which we will use a lot, which is graphic notation. Here's the random variable random variable, so it's big D, whether the person has diabetes or not. Here's the lab that is used for the test. And here's the technician, call it tech, not to be confused with the test. And here's the person for P. And here's the test result. The test result is directly influenced by the disease state. You would hope so. That's why we're doing the test. It's also influenced by particular characteristics of the person, such as their genetic makeup and their behavior. It's also influenced by the lab and the technician, but the lab determines the technician. Technicians typically work in only one lab. These arrows informally mean dependence. We'll later interpret them much more rigorously to mean the absence of independence. Now, do labs affect the test only by their choice of the technician? Namely, some labs have some technicians that are careful and some technicians that are less careful. By choosing a lab, you're choosing a distribution of technicians. Is that the only way in which they affect the outcome? If that were the only way in which they affect the outcome, this picture would be correct. And it would also say that once you chose the technician, it doesn't matter what lab it came from. But it also is possible that the lab has other impact on the result of the test, on whether it's correct or not through the choice of technician, but because of the kind of chemicals they use, the kind of procedures they use. In which case, I want to show that with a straight line here, saying there's direct causality or direct influence between the lab and the test, not only via the choice of technician. What these arrows show is that this test is dependent on all of these variables. But variables themselves may not depend on one another. I would say these two probably do. The nature of the person may have bearing on whether they have the disease or not. These arrows do not mean causality usually when we write them. So we will talk about it at great length, the difference between causality and correlation and dependence. But right now I want to think about it as they express dependence. Sometimes direct dependence, sometimes indirect dependence. All right, let's go back to our poor cancer patient. Well, we don't know if they're poor yet. There's an 80% chance that they're not poor. Question?
Yeah, so originally when we first set up the problem, we said that the 1% error was the technician sort of just randomly flipping a coin or something and then biasing it. But in that case, we originally said that the two tests were independent. So how do you square that away with what we're saying now, that in general, the tests are not independent given the technician error?
They're incomparable. So you're saying we talked about the test. When we talked about over there, we assumed that they're independent of each other. We assumed this. We assumed this, right? And then we went and talked about all the ways in which they are dependent. And the answer is, yep, you're right, the two are not compatible. I made an assumption, it's a wrong assumption. Which means that you as a doctor, when you get your first test result, and if you remember, it tells you that from everything you know, the patient should have, there's only a 20% chance or 21% chance that they have cancer. If you want to do another test, you should look for a test that's as little correlated with the first test, conditioned on the true state of the disease. So you should seek a different lab, a different technician, a different type of test. You can't change the person. I left you with a question at the end of the last lecture. You're the doctor. You got back the positive test result under the conditions we discussed, which means it's a very rare cancer. It's a very accurate test. It came back positive. You did the base calculation. You got 21% chance of cancer. What do you do now? Specifically, what do you tell the patient? Did you think about it? I bet you couldn't stop thinking about it all weekend long. What do you tell your patient?
So, if you had originally ordered two tests, you'd be in a bit of a better situation. But
right.
Now that you know that you think they have cancer, ordering another test is biased by what you already know. And so it kind of messes, like a doctor who just orders a test and then orders the same test based on whether the first test said that there was cancer, that's also an independence issue that you're introducing.
Very, very acute observation. The doctor didn't decide on the second test until they saw the result of the first test. What if the result of the first test was negative? Would they have ordered the second test? Probably not. It's a rare test. It's a rare cancer in the first place. It came back negative. The chance that the person has cancer, we do the calculation, but it's going to be extremely small, even smaller than the original probability of 0.008 in the population. So the doctor would not have ordered the test if the result came back negative. And the point made here is really important. You need to think if the test that you're ordering or the decisions you're making depend on the data you saw, that's different than if you made those decisions ahead of time. One way of making this argument is to say it's kind of overfitting. You're using the data to decide. However, if you're using Bayes' formula, you are still within your rights. You're still being okay because you did the first test, you updated Bayes' equation, you got a posterior, and now you can treat the posterior as your best view of the world, and now you can use that to make a decision going forward. So yes, the distinction is extremely important, whether you decide on the test ahead of time or not, but you're still completely kosher in this state. What I was asking is, what do you tell the patient after one test? They come back to your office. Do you know why you don't order 2 tests? One reason is they're not going to get reimbursed, right? What do you tell the patient? What would you like to be told? Do you tell them there's a 21% chance you have cancer? No, these are real problems the doctors face all the time. Do you tell them nothing? Yeah?
You tell them it's a rare form of cancer and immediately to confirm we like to run more tests on you.
That's what I would like to hear from my doctor. It's a rare, the thing I'm considering is very rare. Well, what I'd like to hear is to get the likelihood table and figure it out myself. But I don't know that that's what most people would like to hear. I mean, this is a real practical problem. It's not a machine learning problem, but it's a very important public policy problem. Do you tell them the test was lost? We need another one? That'll be lying and kind of paternalistic. There's something you can tell them that would be truthful and appropriate. You can say the results were inconclusive, which is true. The results are inconclusive. 2080 is inconclusive. It doesn't mean the test didn't come back fully positive. It just means the results, the outcome, the overall consideration is inconclusive. I still don't know what's happening.
The results might be inconclusive even after the second one.
Yes, they might. So let's try that. Let's try that. We send the second test. You have a question?
Wouldn't the purpose of the test then just to be telling people that it's negative? Because would you ever tell them that?
Well, you may not tell them after the first test, but you'll do a second test.
Oh, you're saying
Yes, I'm not saying ignore it. I'm saying let's do. So let's tell the patient that the result was inconclusive. We need to do another test. And let's do a second test that is conditionally independent of the first test, conditioned on the state of the disease, which is hard to do in the real world because of all the reasons we gave. So to do that, we start with a new prior. Our new prior P of cancer, if you remember, was 0.2085. No, I don't remember 4-digit numbers all the time, only when I use them 20 years in a row. And P of not cancer is, of course, 0.7915. These are our new priors. They were yesterday's posterior, or last week's posterior. Today they are priors. What about the likelihood table? I'm going to assume the assumption of conditional independence is the assumption that the likelihood table is the same as it was last time, which was 0.98 and 0.97 and 0.02 and 0.03, and I may have swapped the rows. I don't remember, so I will not even put the labels here. Now, what is this assumption? Let's talk about it in depth. It says the probability of T2 being positive conditioned on the old prior and T1 being positive and the disease state. Actually, likelihood does not depend on the prior, so I don't need this. Sorry, I apologize. T1 being positive and the disease state. Saying that it's the same likelihood table basically says I can cross this out. Crossing this out is the same as saying, remember our definition of conditional independence. When you allow yourself to cross out one of the conditioning events, that's like saying that this is independent of the one you're crossing out, condition on all the ones that remain. This is the same as saying T2 is conditionally independent of T1 given the disease state. I think the disease state was here. So this is cancer, not cancer. All right, I have no choice but to look up which one is the 2% error, which one is the 3% error.
Positive is the 112.
Positive here. So when the patient has cancer, there's only a 2% error. And when they don't have cancer, there's a 3% error. OK, thank you. All right, so let's calculate the probability of cancer according to the new prior, given that test 2 is positive. Bayes' rule again. In fact, let me write here what it was last T1 calculation. T1 calculation was probability of cancer given the test 1 was positive. And it was the prior, which was 0.008, times the likelihood, which was 0.98, thank you, divide by something that always starts the same way, 0.008 times 0.98, plus 0.992 times, instead of 98, it'll be 0.3. Remember that? Now I'll do the same thing here. The only thing that changes is the prior. Instead of 0.08 here, we have 0.2085 times 0.98. And here it's 0.2085 times 0.98 plus the probability of not cancer, which is going to be significantly less than 0.992. It's going to be 0.7915 times 0.03. So the likelihood component remains exactly the same. What changed are these things. What do you think it comes to now? Forget about the numbers. Just from what you know about this disease, how rare it is, and about the test, how accurate they are, and the fact that we moved from a 0.8% prior to a 21% prior with one positive test. What are we going to move to now? Quite high probability. Did somebody calculate it? Maybe I have it in my notes. Or maybe you remember it, Daniel, from last time. I think it's around 89 or 90 something. You can calculate. It's going to be quite high. Yep, I got it. 0.896. So almost 90%. Whereas here we were about 21%. So we moved from under 1% to 21%, and from 21% to 89%. What do you think we're going to move to if we get another positive test? 100? No, we'll never beat 100. But we're going to get very close to it very fast. There's a way of seeing how the weight of the data pushes us towards the right answer. Let's track what we called the odds ratio. The odds ratio is defined as the ratio between the two possibilities. The two possibilities are here are cancer to non-cancer. starting with before we have the data, just the priors. This is 0.008 divided by 0.992. This is so close to 1, this is about 0.008. 0.081 something, or less than that. It's about 0.008. Now what about the odds ratio after the first test? P of cancer given positive, given the first positive, divided by P of not cancer, given the first positive. That was this number divided by this number. I'm sorry, this number divided by this number. 0.2085 divided by 0.7915. How much is that? You have to add about 25% of this, about a quarter, so it's about 0.25. Yes? What about the odds ratio of cancer given 2 positive tests to not cancer given 2 positive tests? Now it's this number divided by 1 minus this number, which is about 0.1. Now we're at about 89 or 90. Right? No. Divided by 0.9, so it'll be 8.9 to about 9. The odds ratio is what a bettor, somebody who bets, might want to know. Of course, it's the same as knowing the probability of cancer. It's just probability of cancer over 1 minus probability of cancer. But it's a good way of keeping track of the relationship between the two, the ratio of the two. Now, here's the general. Instead of looking at the odds ratio, let's look at the log odds ratio. The odds ratio would be a number, a positive number always, between 0 and infinity. Right? Log odds ratio can now be negative. It could be between negative infinity and positive infinity. Let me do it here. The log odds ratio is going to be defined as a log of the probability of the hypothesis given the data 1 through data n, divided by the probability of the negation of this hypothesis given data 1 through data n. If you use Bayes' rule now, you can open it up in terms of the ratio of the priors and the ratio of the likelihood. This would be the ratio of the priors, prior of a hypothesis, over prior of the negation of the hypothesis. I'm sorry, with the log. Log of the priors plus, now it's going to be the log of the ratio of the likelihoods. Now I'm going to make the further assumption that the likelihoods, the probability of the data given the hypothesis, the data is independent. So I'm going to make the conditional independence assumption that D1, Di is conditionally independent of Dj given the hypothesis for any I and j. And I should use a different. Okay. So I have n different random variables here, n different tests. And I'm going to assume that they're all conditionally independent of each other, conditioned on the hypothesis, conditioned on whether the person had cancer or not. And under that assumption, I can break it down to a sum of the logs of the likelihood of each data item, given the hypothesis, to the likelihood of the same data item, given the negation of the hypothesis. I'm switching back and forth between general terminology, hypothesis, data, and cancer terminology, but hopefully it's clear that they're the same. I can write it explicitly. This is the same as plus the ratio of positive given cancer to, I'll write it T1 positive. Switching back deliberately. All right, I'll write it from the beginning. It's going to be the log of P of cancer to P of not cancer plus the log of probability of positive given cancer, probability of positive 1, let's say the first test, given cancer, the probability of first test being positive given not cancer, plus the log of the probability of positive for the second one given cancer, log of positive for the second one given not cancer, and so forth for as many tests as I have. Now remember these sorry, there's a log here again. These log terms can be negative or positive. What are they going to be in our case for cancer? Is this going to be positive or negative? Is it more likely that there is, I'm starting here. Is this going to be positive or negative?
Negative.
This is negative. This is much bigger than this. So this is negative. What about this? I thought it was positive. So the probability of a positive test given cancer is 0.98. Positive given cancer is 0.98. And probability of a positive test given non-cancer is 0.03. So this is much bigger than 1. So it's positive. And under our assumption of conditional independence, they're all not only positive, but they're all exactly the same value. Now, what is this log odds ratio good for? Suppose you have to stop the test at some point and make a decision. You can base your decision on whether the log odds of the posterior, which is what we wrote here, or the log posterior odds, log odds posterior, I don't know, is positive or negative. Right? If it's negative, it's most likely not cancer. If it's positive, it's most likely cancer. If you're placing bets on it, not a nice thing to do, but if you're placing bets on it, the size of the bet or the risk you're taking or the calculation of how much you're going to get in each case will depend on specifically the log odds ratio. But if you're just making a decision, more likely, less likely, just make it based on whether it's positive or negative. Here's the thing. Before you do any tests, negative. You don't know anything except the general population distribution. Therefore, you'll say not, more likely than not, it's not cancer. After you do one test, you have to add up the negative and the positive. And we know that the answer is going to still remain negative because we know that it's 21% only, less than 50%. As you do more and more tests, you're adding more quantities. At some point, it's going to go above 0. This is a demonstration of the difference between prior and likelihoods. Prior is fixed. Its contribution to the log odds is fixed once at the beginning. A likelihood, you can get, as you get more data, you're adding more terms to the likelihood. So in the end, the likelihood terms will dominate. Was a question here?
Does the number give any value, or is it just a sign that, okay, if it's changing sign, it's a good thing for us?
So I addressed that a minute ago. The answer is yes, it does give value. If it's 0, it means your posterior is 50-50. If it's negative, it means your posterior is biased more towards not cancer. If it's positive, towards cancer. Do you use that? Yes, I think you do. You have to decide how confident you need to be, right, before you stop doing tests. And that depends on your actions. on what you're going to do based on that, and on the repercussions. What's going to be the benefit or the damage of making the wrong decision? So you need to take those into account. This falls into what's called Bayesian decision making. But the short answer is yes, of course it depends on the number. Yeah?
Why is it on this board we're doing the probability of the test result given the disease for the log odds ratio, but then when we did it on the other board, we did it for the two variables reversed?
Other board is which one?
Oh, sorry. So there's cancer given positive.
Where?
Like right in the log odds ratio, or the odds ratio in the middle, where it's probability of cancer given positive.
This one?
Positive, yeah.
Oh, I was just showing the general form of log odds ratio. You can do log odds, you can take the log of the ratio of the posteriors, you can take the log of the ratio of the likelihood, and you can take the log of the ratio of the prior. What I was trying to show here, and thanks for pointing it out, is that this is equal to the log ratio of the posteriors. So in this case, if I stop it here, it would be exactly what you said. Positive, positive, given cancer, divided by positive, positive, given not cancer. So just like if you think of posterior as being related to prior and likelihood, this is a very nice way of capturing it. The log odds for posterior is equal to the log odds of the prior plus the log odds of the likelihood. Did I get that wrong?
Isn't the hypothesis supposed to be C?
The hypothesis is supposed to be C or C bar, right?
Yeah, and on the left-hand side, it's the number of tests that you perform.
I'm sorry?
So it's C given positive, positive, right? No.
No, this is the posterior. This is log odds of the posterior. I'm sorry, I should have done it more rigorously. All I meant to say here, oh, wait a minute. No. I reversed it. Yeah, it's posterior. I just wrote the wrong thing here. I'm sorry. It is posterior. I mean one thing and I write another. Sorry. C++ and C++. So your question here is why did we do something else? No, it is the right thing. When I copied it wrong. I'm sorry. Okay, take home message. The log odds of the posterior can be broken down as the log odds of the prior plus the log odds of the likelihood. That's a take home message. Let me not take a question. You can come to me after class. I want to use the remaining minute I have to ask you about the prior. Was this the right prior to use? When I told you the story, I said that the cancer is known to be prevalent, to have the prevalence of 0.008 in the population. Namely, that of all the people in that country, if you somehow were able to determine completely accurately who has it, who doesn't, you will find that 0.8% of the people have it. And that's how I derived my prior. And my question to you now is this the right prior to use? Yes?
People who come to the hospital
People who come to see a doctor might have a higher probability than someone plucked randomly from the population. So the question to ask is, why did the person come to see me in the first place, me being the doctor? Why am I doing the test? Now it could be that I'm doing the test because it's a standard procedure to do this test to every person when they reach age 50 and the prevalence of disease is 0.008 among people who are 50-year-old. In that case, it's called a screening test, and the prior is this prior is the right prior to use. But it could be that I'm doing the test because the person came in and complained about symptoms that made me think of that disease, in which case it's the wrong prior to use. Could make a big difference in the interpretation of the results. So because of that, in standard medical procedures, what you're supposed to do for a given test depends very much on whether these sets were done specifically to detect that condition or were a byproduct of some other test or some other screening. Sometimes you do a CAT scan of the lungs because you suspect something, and the picture included some part of your stomach, and you notice something in the stomach. That means something completely different than if you suspected something in the stomach, you send someone to do a CT scan of their stomach. The priors are different. All right, I need to let you go. We can